What I have here today is a new device from Snap-on called a sensor simulator. Really going to help instructors in their class when they want to show a student technician what a particular waveform pattern looks like. This is displaying waveform patterns off of what would be a 2012 BMW 328i with a 3-liter V6 N52 KP engine. And what it does is it sends out a signal that resembles the different sensors on the vehicle, such as wheel speed, cam, crank, pedal position sensor, throttle position sensor, all of these signals. What I'd like to do today is we're going to go through these different signals, but while we're on them, I want to give you a short tech tip when you're actually testing on the vehicle, things to look for, and what are the features and the benefits of looking at these various patterns. We all want to whip the world with our scan tool, but let's face it, scan tool is process information. You'd much rather see the information at the same speed that the computer sees it. If you have a trouble code, you're typically looking at, is it a defective sensor? Is it a problem in the wiring, high resistance, short to power, short to ground, open circuit? Or is it the module, the computer itself? And that usually means that you're going to be doing some pinpoint testing utilizing the lab scope. I'm using the Zeus, the latest Snap-on platform in diagnostics. Embedded in the Zeus is a very powerful 4-channel lab scope. The yellow trace is the crankshaft sensor. The green trace is the camshaft sensor. So I can look at crankshaft sensor and camshaft sensor at the same time. Here's a tip. Many vehicles, either the power supply to the crank and cam or the ground supply to the crank and cam are common. So if there's a large voltage drop in the power feed, power supply, or ground side of the sensor, it's going to affect both of them. It's not a bad idea to get yourself tuned to and accustomed to looking at crank and camshaft sensor at the same time. The other benefit of it is if you have a known good pattern on the particular vehicle you're working on. For example, if you know the relationship where the cam's leading and trailing edges fall in relationship to the crank sensor, as the computer, or possibly you with a bidirectional test on your scan tool, if you command to advance the timing, the camshaft sensor should shift to the left. If you choose to retard the timing, it should shift to the right. Now, if you have a known good pattern, let's say at idle, and you can see where the leading and trailing edges of cam to crank relationship fall, it won't take very long, the amount of time to connect to the cam sensor and the crank sensor, and you got a pretty good idea if the timing chain has jumped time. So hooking directly to that. But the downside is these patterns can sometimes be difficult to find. My suggestion is International Automotive Technicians Network, Thompson Automotive Labs. You'll have to do some web internet searching to find a known good pattern. Or once you have a known good pattern of a particular vehicle that you're working on or a fleet of vehicles, do a printout. Put it in a file. Now you can go back and use it as a reference to see if that 4.6 Crown Vic police cars that you work on all the time has jump timing. So this is a lot of value in being able to see the relationship between crankshaft sensor and camshaft sensor.